Hi, this is part 5 of my series on parametric differentiation. So this is try now 40. Of course, if you do have access to the textbook, then you can also follow from the textbook. I think this is page 510, I believe. But if you don't have access to the textbook, you can just follow and try to do the questions also by yourself. It says the diagram shows the curve with parametric equations in terms of t. You have x is equal to 2 minus the cosine of t. Then you have y equals to 1 plus 3 times the cosine of 2t. And t is an angle that is between 0 and pi radians. So we need to find dy dx, and then we should show that it gives us that. Of course, I can just as well start here with part A, since it has got so many faces of us. I can say, okay, this is x is equal to 2 minus the cosine of t, and I'm going to have dx dt. Okay, the derivative of that is obviously going to be minus sine t, and then this is just going to be sine t. That's it. Okay, sine t. Right, sine t. So therefore, dt dx will be 1 over sine t. Hope that makes sense. Right, the next one obviously that we need to find is this one over here. We need to find y equals to that. So let's do that over here. So I'm busy with part A. So if we do y equals to that, that's obviously going to be give it time to save. That's going to be, of course, there is one more thing that one can do before one just go ahead and okay, but anyway, this should be fine. So you can say dy dt is going to be derivative of 1 is 0. That's 3 times the cosine of the cosine. The derivative of the cosine is minus sine of 2t times the derivative of the inside times 2. So this gives us minus 6 sine 2t. Right, so we're going to multiply those two, dy dx, therefore. In fact, maybe one can just go ahead and clean this up a bit. And the reason why I do that is because I'm looking at what is it that I'm supposed to find, and I'm supposed to see that I must have something as cos, but I have got 1 over sine t and sine double angle here. And I hope you still remember how that double angle can be written. It's minus 6, and then you have got 2 sine t cos t. That's how you can write it. So obviously this becomes minus 12 sine t cos t. Right, so you have got this one over here and this one over here. So you're going to multiply the two of them. So you're going to say, therefore, dy dx is going to be, let's take dy dt, which is negative 12 sine t cos t, and we're going to put it all over sine t. Right, so what does that give us? It gives us that sine t is cancelled, and at the end of the day, you're going to be left with minus 12 cos t. So the correct answer then is minus 12 cos t. Right, this was obviously this is what we needed to find, so we are on the right path. Okay, good. So this is dy dx. Now part B of the question says find the coordinates of M. Now is that M a minimum point? Good. If M is a minimum point, okay, if M is a minimum point, then that point, the gradient at that point, dy dx will equal to 0. So here we're going to have dy dx here is equal to 0 because it is a minimum point. Okay, they say the curve crosses the x-axis at those 2 points. Okay, right, so let us find then the coordinates of M. And to find the coordinates of M for part B, maybe I need to bring part B in there. So let's take part B. Okay. Remember we said part B is when the derivative is equal to 0. So that's when that is equal to 0. So we're going to say minus 12 cosine of t is equal to 0. Now, if you were to calculate it, now you obviously are going to find that the cosine of t will equal to 0, because 0 divided by negative 12 is just equal cosine of t is equal to 0. Now, I'm going to bring in, again, my graph. It's always easy and nice to have. So what do we know? Well, we know that the cosine graph starts here, oscillates between 1 and negative 1. 1 being here, negative 1 being there, not negative 2, my God. So that's going to be negative 1. That's 0. That's the x-axis, and this could be my angle. That's the x-axis, that's and that is y-axis. Now, the values that we have over here, this here is pi over 2. This here is pi. And this here is 3 pi over 2. And then obviously, right towards the end is 2 pi. So what is it that we are looking for? We are looking for these values where the value of that graph is 0. Okay, but y is equal to 0, right? Whatever is in this side, where you have y equals to 0. Well, it's basically that. So t is then pi over 2, or t is 3 pi over 2. Now, before we continue, there's something we need to consider. Let's just go back to our part A, or what we had. They are saying that this is very important, that t is an angle that is between 0 and pi radians. Okay, and because of that fact, we need to be able to disregard one of those things. Let me just bring that out. So when we are looking at this, they're saying t is that. So that would imply that t is only going to be pi over 2. That is what we're going to look at. Okay. Now, it's important to understand they are looking for the coordinates of x in our graph here, the coordinate of m. So what is the value of the coordinate of m? So we are supposed to look at our two equations, which is if t is equal to pi over 2, then x will equal to and y will equal to. So we need to go find what our value of x was. X was 2 minus the cosine of going to be pi over 2. Well, that's going to be 2 minus pi over 2 is 0, so that is 2. And y was 1 plus 3 cos of 2 times pi over 2. Now, very important to know that the cosine of pi is negative 1, so that's negative 3 plus 1 is negative 2. So that gives you negative 2. So of course I'm using also my graph. Okay, I know that if I'm here at pi over 2, this one here, pi cosine of pi is going to be here at negative 1. Right. Good. So what are the points? What is the point? The point that we have is the point x is 2 and y is negative 2. So this is the point M, which was the point that was on the curve that they asked us to find the coordinates of. Right. Then there is a C part. Perhaps I need to bring the C part down. they say find the gradient of the curve at points. Let's just copy that over. Let's just copy that over, and I'm gonna have it here. And there's another thing that I'm going to bring. I'm going to bring the whole curve. I'm going to bring the whole curve as it is. Just clean this up a bit so my curve doesn't have so many things that I need to worry about. So I'm going to bring my curve just so that I can have reference to it. So see what they are asking me. They're saying find the coordinates, the gradient of the curve at that point P and also at the point Q. Now, what is happening at those points P and Q is that the y values are 0. Okay, at points P and Q, as you can see, at this point here, and this point here, at those points, y equals to 0. So if just write it down. At points P and Q, y equals to 0. So remember our equation was y equals to 1 plus 3 times the cosine of 2t. That's what it was. Right, they are saying then y equals to 0. So we're going to have to let that to 0, or y equals to 0. So 1 plus 3 times the cosine of 2t is equal to 0. Now, let's see if we can clean this up a little bit. So this is 3 cosine of 2t is equal to -1. This will give us that cosine of 2t is equal to -1/3. Now, what do we know? We know that the cosine will be negative in quadrants. So we know that cosine is negative in quadrants 2. Okay, let's take that away. It's going to be negative in this quadrant and also in the third quadrant. So we are going to find our reference angle. Let's suppose we call it, let 2t be, let's say it's a k, okay, or theta. Then the inverse of a third, we're going to find the acute basic angle, making sure that our angles here is in radian mode. So it's in radian. So the inverse cos of 1/3. Well, that's going to give me some decimal value, which I can just as well capture and paste. This is what I'm going to get. So my solutions will be in the second quadrant. In the second quadrant, all over here, the angle that I'm going to consider is going to be pi minus theta, or minus k. Okay, I can decide this to be my k. Okay, pi minus k. So in the second quadrant, where cosine is negative, I'm going to say, okay, 2t is equal to pi, take away 1.23095, and so on. And what I need to do in order for me to find the value of t is simply find this difference and then divide that answer by 2. And once I do, I get 0.9553166, and so on and so on. Radians. Then also, very important that you do understand something is that in that quadrant, we are not going to consider, of course, from our domain, our original domain, I'm not going to consider these two, because our original domain is only from 0 to pi radians. So when we now have calculated the value of t, and what we need to find the gradient of the curve at P and at Q. And in order for us to do that, we need to say, okay, what was our dy dt? I mean dy dx. Dy dx when t is equal to 0.9553 and so on and so on will be, remember it was minus 12 times the cosine. So it's going to be the cosine of 0.9553 if I have to do that myself. And then we are going to get, it's very important that you do understand something as these curves are. Whatever the gradient of this, the gradients will be equal but just with opposite signs. So if the gradient of P will be negative, the gradient of Q will be positive. So my answer will be positive and negative here. Okay, so let's grab the calculator to see what that value would be. So we're going to have, let's divide that answer by 2, was it? No, we had pi minus our answer. Oops, my goodness. We had pi minus our answer, and then we divided that by 2. Okay, I just want that value to be in my calculator. Right, so I've got negative 12 times the cosine of my answer over there. Well, that gives me negative 6.92. Okay, 8. Right, so let's just grab it again, capture it. Right, so our answer will be, and I'm going to write it underneath just to keep the space. And then the gradient at P will be negative 6.93, and the gradient at Q will be 6.93. Okay, just be making sure P will have the negative one and Q will have the positive gradient. Those are the two solutions to the question that we were looking for, and yeah, but it's a very interesting question as it is. Right, this is the end of the 5th part of my series on parametric differentiation. Then stand by for the next video, which is going to be my last part on parametric differentiation.